Hello and welcome to this SimScale demonstration. My name is David and I'm going to be taking you through an electronics cooling application on the SimScale platform. Specifically, we're going to be looking at a passively cooled LED module using conjugate heat transfer analysis to optimize the heatsink design. So here's a little rundown of the project details for this CHT application. We're going to be looking at a LED module with 7 LED diodes or chips totaling 7 watts of dissipated heat. And the objective is, as I said earlier, to optimize the design of the heatsink, ensuring the best quality lighting performance as well as the LED lifetime. The result of interest that's going to indicate both of these two parameters is the junction temperature of the LED. So that's really going to be our result that we're going to get to as our result of interest. So the simulation, the analysis type that we're going to be using is a conjugate heat transfer simulation. So this is a coupling of your flow physics, so based on finite volume method CFD, coupled with heat transfer capabilities as well. So that gives us the ability to look at conduction within the solids, convection within the fluid, air in this case, and also radiation between the solid surfaces as well. Now we're going to be running a steady state simulation and using laminar flow rather than employing a turbulence model. And as I said earlier, the result of interest is really going to be the LED junction temperature as well as a general understanding of the convectional flow field as well. So here is the CAD model that we're going to be using, or one of the design variations that we're going to be looking at. As you can see, it's a finned heatsink with 7 diodes placed within the bulb. We want to compare a number of different heatsink designs to understand what gives the best cooling capabilities. And then as a secondary piece of information will be actually the amount of material required, because obviously that's going to have a bearing on the cost of manufacturing as well. So these are the 3 different designs that we can have a look at. And what I'd now like to do is jump into the SimScale platform so that I can show you both the results of a single design, and then we'll set off a simulation together for the next proposed design. So here we are in the SimScale platform. We're firstly having a look at the results to our proposed design 1, where we can see the heatsink on the outside here. And you'll notice that we're running a quarter model, so we're taking advantage of the symmetry of the model, so that then we can really optimize the run times of our simulations. So there's no need to run the full model if it's symmetrical. So here is the heatsink. We can see the temperature distribution across the heatsink. You'll notice here on the bottom that we've got the temperature actually plotted on the solids, and then in the fluid region on this cutting plane we have the velocity magnitude as well. Additionally, I've put a few particle traces actually within the bulb itself, so that we can see what's happening in terms of the natural convection within this small air volume as well. Our result of interest is really the junction temperatures, and we can find these junction temperatures. If we zoom in on the diodes themselves, we can pick points within the model to inspect temperatures, for example. So we're looking at the temperature of 77.25 degrees Celsius on the case surface of the LED. So that's not going to be the exact junction temperature. You'd want to then back calculate the junction temperature using the thermal resistances provided by the manufacturer to get from your case temperature back to the junction temperature. So now what I'd like to do is show you how to set up a simulation like this, and for that purpose we're going to set off a new simulation for the next design candidate. So we can go over here to our simulation tree and duplicate the simulation we've already done and simply apply it to the next geometry. Okay, so if we go to geometry here, we can then select from the geometry list, from the geometry tree, any of the CAD models that we've loaded into the SimScale platform. So let's go for our version 2, the design 2, and then we can set off this next simulation. So as you can see, it's loaded into the viewer. And we can see that we've got some bulkier heatsink fins with a larger spacing as well. So when I started off that, when we assigned the new geometry, what it firstly did is automatically found the interfaces between both the solid parts and also between the solids and the fluid regions as well. Okay, so that's done automatically for you, and we just need to worry about the actual design parameters. And what we're going to do is then go through and assign these design parameters. So that being the materials, and then the boundary conditions, which is dictating the physics of simulation. So our carrier fluid is going to be air, so we can apply that both to the external air volume as well as the internal bulb volume as well. So then we've got our air. So now let's assign the solid materials as well. So we're modeling the diodes themselves as silicon capped LEDs. We're modeling the heatsink as anodized aluminium. The PCB board is a metal core, so an insulated metal substrate board. And the wire is a copper wire. We've got a ceramic substrate as well, and then a polycarbonate screen. Now, in terms of the physics, the boundary conditions for this simulation, we're going to be running this as natural convection inlets outlets. So that allows the air to enter and escape through these surfaces. So we're modeling the LED suspended in a large volume of air. So the additional physics that we need to add is adding the dissipated power to the LEDs themselves. So for the full LED, the one that isn't cut by the symmetry planes, we're applying 1 watt, and then we've got our half LED 0.5 watts, and the quarter 0.25 watts as well. Then it is time to set off the simulation. So we can leave the rest of the simulation control up to default. So meshing and simulation control, we can leave up to defaults in a simple simulation like this. So we get an estimation of the time it's going to take for the simulation, as well as the amount of compute resources it's going to use. So if we're happy with that, then we can start the simulation. So now that's up and running in the cloud. We're not going to wait for the results here. I would like to show you the results as a comparison between all 3 designs, so that you can get an idea of the sort of design feedback that you can get out of SimScale simulations. So let's jump back into the PowerPoint. So here we can see a side-by-side comparison of the temperature distribution for each of the 3 designs, and we can clearly see that the original design is really not optimized for the flow situation. So it's not doing a great job at cooling these LEDs. Whereas design 2, we have a nice low and uniform temperature distribution across the heatsink, the aluminium heatsink. And we can actually understand why this is the case as well by looking at the convective behavior. So if we look at the original design here, we can see that there's actually not that much penetration of the airflow to the center of the heatsink channels, whereas in the proposed design 2, we have a much greater amount of flow within the heatsink channels, thus increasing the cooling capacity. And if we look at the junction temperatures themselves, or the temperatures on the diodes, then we can clearly see the benefits of the proposed design 2 in terms of the heatsink performance. So both in terms of cooling capacity, which is going to ensure the good lighting performance as well as long lifetime, and also we're going to be having gains in terms of reducing material costs using proposed design 2. So that was a quick introduction into the electronics cooling capabilities of SimScale applied to an LED application. And we can really see how SimScale allows designers and engineers to gain design feedback from running multiple simulations using cloud resources. Thank you very much for watching.